the Papadopoulos. It's from 10 to 12:30 with a tea break at 11 o'clock. And he will tell you all about it.
Okay.
And we have some discussion closing at the end. Thank you.
Okay, thank you very much. I'm always sad when it's the last class, because I'm used now to all of you, to your faces, to your questions. All of you are interesting. I prepared some projections for today, but before that, I thought I have to do a small compliment. In fact, two things. One thing is about transverse measured foliations. So we know what is a measured foliation. This is a foliation, and I can measure the kind of length. There's a measure on each transverse line, and it's invariant. So this transverse segment here and this transverse segment, there's a natural map between them. I send every point to the point which is on the same leaf, right? And this natural map is measure preserving. This is a measured this is transverse measure for the foliation. There are more general transverse structures. For instance, a foliation is said, instead of being transversely measured, it can be transversely projective, and meaning that these maps are projective. These local maps are projective, or they are much more complicated transverse structure. Anyway, so this is a transverse. And then we talked about, I showed you a picture, and we talked about now transverse measured foliations. And we said that transverse measured foliations are like this. Transversality is just a mathematical notion, which means that they intersect, with a definite angle, if you want. So this intersection is not transverse because here it's tangent. Okay, so transverse means just that. Transverse means that you can think of intersecting with a positive angle. So transverse measured foliations. So we have two measured foliations. So locally it's like this, but then I have to decide or at these and so on. Okay, so I have transverse measured foliations. We talked about quasi-conformal maps. These are the maps which send the local infinitesimal circles to infinitesimal ellipses, and this ratio here, is bounded. This is the meaning of quasi-conformal. So, and what I want to make the relation. In fact, we said that there is a Teichmüller distance on Teichmüller space. This is much before. Describe geodesics for this metric. So when I started this course, I said, okay, we are going to define a metric and on some space, and what are the good questions after we define a metric? One of the good questions is, can you describe the geodesics for this metric, right? We did this for the hyperbolic plane. We did this for the Euclidean plane. On the sphere, we said geodesics are. So now I have a metric on Teichmüller space. I have two metrics. We define two metrics, the Thurston metric and the Teichmüller metric, which I defined. And okay, so what is the relation with transverse measured foliations? So first, let me note that a surface equipped with what? With two transverse measured foliations carries naturally a metric. So you see, the surface is like this, a surface, and it is filled with this measured foliation, and it is filled also with the other measured foliation, which is transverse. Now, I say that this surface is equipped with a metric. Is there a natural metric you see here on this surface? Yes. No, not necessarily the taxicab metric. No, because, I mean, no, it's not the taxicab metric. It's something more easier than the taxicab metric. Because, you know, to go from here to here, I don't need to do this. I just follow this. I just follow this straight line, like in the Euclidean plane.
But what is the straight line?
Yeah, this is, what are these? What is this metric? A pair of transverse measured foliations define a metric on the surface. And I'm asking, what is this metric? Well, I take a point here. I have these natural squares. I can send them to squares in the Euclidean plane by isometries, in fact, because this is Euclidean and this is Euclidean. I mean the distances when we said we have a transverse measure, the transverse measure is Euclidean, right? There's no other way here than sending this to this portion to a portion of the Euclidean plane by sending horizontals to horizontals and verticals to verticals. Here I have a notion of horizontal and vertical, and then I have a notion of length here. I have a notion of length which comes from the transverse measure. Okay, so in fact I have charts. I have charts for this surface equipped with these transverse measured foliations, and the coordinate charts are Euclidean isometries because of this invariance of the. If I take another chart like this, you see this is the same length, and so on. Okay, so let me write this here. Carries a metric. Which is Euclidean, except what? Except, yes, at the singularities, because I told you what happens here, but I didn't tell you, here at a neighborhood of the singular point, I cannot send it isometrically to the Euclidean plane, right? Because here I have, it is like I'm gluing I am gluing 1, 2, 3, 4, 5, 6 rectangles along a single vertex, and I destroyed the Euclidean metric. So a Euclidean metric on the complement of the singularities and at the singularities, I have a special structure which, you could think about this at the singularities. So this is called, in fact, this is called a singular flat means Euclidean. Singular means I have singularities. A singular flat metric with cone-like singularities, and I can compute there's a cone angle. I can compute the cone angle at each singular point. Let me take a very simple example. So this is a surface, the surface of this parallelepiped. Here I have foliations perpendiculars to the boundaries of my rectangle. Here I have two foliations, so on. I'm taking a Euclidean parallelepiped, and I declare that these foliations, these two transverse foliations, are measured foliations. Since I want to say that the transverse measure of the arc of this arc, you see, is exactly the Euclidean, its Euclidean measure when I project it on one of the sides, and I do this for when I do this for all these arcs. I mean, I can continue on the surface. So this is an example of I call this a singular flat structure, singular flat metric. This is an interesting example of a singular flat metric. It is not Euclidean. It is Euclidean with singularities. Each point here, or even on the edges has a Euclidean neighborhood, except at the angles. At the angles, there's no Euclidean chart which sends this to the Euclidean plane, because here I have a singular point where the total angle, how much is the total angle around my, so an insect sitting here, he looks at all the directions, at all his horizons, and he measures the total angle around him. So how much is the total angle? 17? What did you say? 3 pi over 2. 3 pi over 2. This is why. So somebody can live on this parallelepiped, but when he arrives at this point, the total angle at the horizon. So this is why it's a singular metric. 3 pi over 2. Somebody told me 3 pi over 4. Did you say 3 pi? Okay. No, because I don't mind, because I'm like this. Okay, 3 pi over 2. Okay. So let me say several things now again. No, let me first finish with it. So there's this Teichmüller metric we talked about, and I said I want to tell you how are the geodesics of the Teichmüller matrix. So a geodesic means, I mean, it means many things, but in particular, I have to tell you a path in this space of matrix, right? And then I will tell you that this path is geodesic. So I come back to my general surface equipped with two transverse measured foliations. What can I do with what is the simplest thing I can do when I have two transverse measured foliations or one measured foliation? If I have a measured foliation on the surface, I can say, okay, I obtain another measured foliation by multiplying the measure by some constant, right? Okay, so in principle, this is kind of box in my measured foliation. If I multiply the transverse measure by 2, then I want to imagine the new metric, in fact, as 2 times larger, so like this. So in terms of the local charts, I'm sending the new local chart for my metric will be extended by 2. Will be multiplied by 2. Okay, so here I have two measured foliation, which are transverse, and I want to treat them equally in the same way. So I will shorten the one and narrow. I will make the second one more narrow. So there is a natural map. I divided the other one by 2. Okay, I did this, in fact, because I want to keep the area of the surface the same. So the first thing you understand is that I obtain another surface. I'm obtaining another surface from the geometric point of view, even if the surface will not change topologically. I am obtaining another surface. The second thing I want you to notice, you have to imagine, is that okay, I told you this change of coordinates, which change the Euclidean structure at a point which is not a singular point, but you must imagine that okay, all these things I'm doing are compatible at singular points. At the singular points, I'm doing the same thing on all these sides, so I get the required result. That is, I get a singular flat structure with the required singularities. Okay, so this defines a path that is a continuous curve, a path in what? Where is this curve? Yes, in my space of metrics, that is in my Teichmüller space. Okay, this defines a path in Teichmüller space. And what I'm saying is that this path is a geodesic for the Teichmüller metric. This is a very important result, in fact. So this Teichmüller metric, I described you some geodesic paths, and there's a Teichmüller existence and also uniqueness theorem. Let me just state it here. So this is also proved. This was proved by Teichmüller. Existence and uniqueness theorem. Any 2 points in Teichmüller space can be joined by a unique geodesic. I mean, it is understood here that for any two, so you remember the Teichmüller space is a distance between two surfaces, and these two surfaces in this setting are complex surfaces. They are not metric surfaces, they are complex surfaces. We are measuring distances, quasi-conformal distances. We are measuring what is the best map which deforms, which is close to a conformal map, which is not, in general, it is not conformal. The surfaces I'm talking about are Riemann surfaces. They are not metric surfaces. The theorem there says, well, I take two surfaces, like two Riemann surfaces. I can construct a pair of transverse measured foliations on the first surface such that the complex structure induced by this metric is the one of this surface. Okay, these are complex surfaces, and a metric induces. I mean, when you have a metric, then you have an underlying notion of angle, and the notion of putting a complex structure on a surface is just a way of measuring angles. Okay, so the theorem says that I can find a pair of measured foliations and a path in the space of measured foliation. This path is, this path is, I said here I multiply by 2 and I divide by 2, but then I can multiply by t and divide by t. This path is a geodesic. This path is the shortest path in Teichmüller space.
Is this independent of the foliation that we choose?
No. For each two surfaces, I give you two surfaces, and the theorem is an existence theorem. It says there exists a foliation on this surface and a transverse foliation. The two foliations depend on this surface and on this one, because they give you the direction on which you have to stretch and contract to arrive to the other surface. Yes. Maybe there's a last thing which I did not explain to you, and which now I think is important to emphasize. What is a geodesic? Mm-hmm. So here I have, you see, I have only a geodesic. You know what is a geodesic in Euclidean plane, in hyperbolic plane, in the sphere. And now I'm talking about geodesics in complicated spaces, in fact, which, I mean, this Teichmüller space and the Teichmüller. Yes, tell me. Well, yes, it has to exist. It has to exist. So in the existence theorem, it says that geodesics exist in the theorem. It tells, yes. Sometimes geodesics do not exist. Yes. shortest paths do not exist in some. I mean, in general they exist, but let's say in some. Okay, so what is a geodesic? What is a geodesic? What is a geodesic here? Somebody can have an idea? I want a geodesic, so I just have M with a distance, let's call it X, a metric space, and I have 2 points in a metric space. And I have a path from one point X to a point Y. So we will suppose that the space is path connected in order I will define a geodesic in terms of a path. So I have a path. I want to say that this path is geodesic. So I suppose the space is connected by arcs.
We should take the infimum of all the paths, length of the paths, and
this is very good. Yes, and you? Its length is equal to the distance between the points. Yes, yes. This is also very good. It's a path such that its length is equal to the distance between the 2 points. So I have 2 very good answers. The thing is that, okay, you must define the length of a path in an arbitrary metric space. So this is not, yeah, this is, I mean, it is something. I mean, you have to prove something to have a well-defined notion of length on what sorts of paths. So you will say, well, do I have to take differentiable paths to define the length? And then you say, okay, but in fact, then my space must carry a differentiable structure, or and then you have to say that you have to take approximations of lengths of paths to the minimum. Why does the minimum? I mean, it is very good. It is very feasible. You have to use Ascoli and things like that. There's a very simple definition. So a geodesic in X, well, it's a path that is just an image, just a map gamma, say, from some, yes, just a minute, into my space X, some interval of the real line into my space X. Yes, what did you say? Somebody said something?
Distance between X and Y. Closed interval 0, the distance between X and Y.
Yes, distance between X and Y is equal to, yes, but is equal to what? You want the distance between X and Y? So your friend says that I want this distance to be the length of the path, right? This is what he said, and I said this is more complicated. No, the definition is simpler, in fact, such that for any, well, 3 points, I take 3 points, x1, x2, x3, in that order in AB. I take 3 points here in that order, then I have what? Yes, tell me now. Yes, right. I have dx1, x2 plus dx2, x3 equals dx1, x3. So this is a characterization of, I'm using this as a definition, but it's a characterization of geodesics in Euclidean plane, in fact. A Euclidean, so if I take three arbitrary points in the Euclidean plane, I know that the distance here plus the distance here is, well, less or equal to the distance here, right? This is the triangle inequality. But here I'm saying that the triangle inequality is an equality for any 3 points on that path. So, and this is exactly a characterization of the straight lines in the Euclidean plane. A line is a straight line if and only if when I take 3 points, x2, x3, then the 3 distances satisfy the triangle equality instead of the triangle inequality. This is the simplest definition, and it is the definition of a geodesic in any metric space. Then you will say, okay, but some metric space, like I take just the union of these 3 points. So what is there's no path, there's no continuous path from here to, so in X. So this is for connected by arcs. Yes, it must be a metric space connected by arcs, and this is the general definition of. Wait a minute. Yes, you are right. You are right. You are right. Instead of x, yeah. This is gamma. You are right. Completely right. Thank you. Yeah, this is a mistake. F of gamma of x1.
You can as well put there in gamma x.
And here you have to put gamma x2. Yes. Thank you. I missed this. Gamma x3. Yes. Thank you. Yes. In fact,
Because of the order.
yes, because of the order. Because of the order, this order is very different. This order, if you change order, then here I put x1, x2, and x3 the names of the points on the image. So
Order is in AB.
No, but this will also be gamma x1, gamma x2.
No.
Only x1, x2 are.
yeah, because the picture I drew here, I put x1, x2, x3 as the points, whereas here I have, so I should take T1, T2, T3, and then x1, x2, x3. Yes, I'm sorry. Okay. So now you have, yes.
So not a closed geodesic on a surface. Sometimes the x1 and x2
Yes.
and with other ways.
Yes. In fact, he has a very good. So there are this is the definition of a geodesic. So yeah. So when you have closed geodesics and so on, then you say that these are locally geodesics. Because yes, you see. So your friend here is saying, okay. So this is an abuse of language. When I say. Suppose I take a closed geodesic here, and I take 2 points. Well, I have on one side, yes, this is distance minimizing. This minimizes the distance between the 2 points. The big one, the big arc does not minimize the distance, but this is so. In general, we say that this is a geodesic, and then the closed curves are local geodesics, but we forget the term local, yes, because we will deal a lot with closed curves, yes. Okay, so this is one thing I want to say about pairs of measured foliations, transverse measured foliations. So maybe I want to.
Are these foliations due to Teichmüller or it's someone else?
Yes, no. He introduced the foliations. He introduced the measured foliations. Yes. So you see, so there's this. I will talk about this later, and if you remember, there's this Thurston metric. If you remember, it was first Thurston distance, a distance between hyperbolic surfaces. This is the original. I explained. I will talk about this later, but I will recall. But this, I have a distance between hyperbolic surfaces. So now, and you remember I was considering best Lipschitz maps between hyperbolic surfaces and minimum of Lipschitz constants of Lipschitz maps and so on. And then I said we have Lipschitz maps between ideal triangles, and then we make Lipschitz maps between surfaces and so on. In fact, when you have learned this, and when you know the existence of these singular flat metrics, then naturally comes the problem: what about Thurston metric on the space of singular flat structures? Singular flat structures on a surface. So I have a singular flat structure. I have a singular flat structure given by two measured foliations. I have a space. I can make it a space, in fact, of singular flat structures, because I can vary the singular flat structures and so on. So first question: what is the best Lipschitz map between two singular flat structures? This I cannot give you the answer because it's a research problem, in fact. It is very natural, and everyone working on Teichmüller theory who knows about Teichmüller metric and Thurston metric, he says, okay, but now instead of, because the distance between hyperbolic surfaces, so I'm taking about this, about surfaces with hyperbolic metrics, whereas here, you see the Teichmüller metric, this is related, I explained to you, this construction is related to Teichmüller metric, but Teichmüller metric does not worry about the actual metric on the surface induced by these foliations, since we only need to consider the complex structure. Teichmüller metric is concerned with the complex structure on a surface, not with a metric. The metric comes because, okay, there's a natural way, and a fruitful theory of transverse measured foliations, which give a metric, but I'm not going to do anything with the metric, but except with the complex structure. Now you say, okay, but now I want to worry about the metric. And I have all this space of singular flat structures on the surface, and I want to mimic Thurston's theory for this space of singular flat metrics. So how can I do? I thought about this with my collaborators, and we don't have anything interesting on this. But I think that this is a subject which is a good subject. Good subject for someone who has time and who can spend time on this. We have some results on. We have some results, you know, on like subsets of the plane, which are, I think I showed you this. I showed you this picture here, which are rectangles of the following form. So Euclidean rectangles, which you glue like this, and they are equipped with singular flat structures. So what is the Thurston distance between this one and this one? And how can you describe the geodesics? So just in simple cases. but not in the general case of a singular flat structure on a surface. This needs work, in fact. Okay, so this is a question. Yeah, before the yes.
You gave inequality WP metric less or equal to K1 of custom metric less or equal to K2.
Yes.
Second
Yes.
from that relation can we say anything?
No, because that relation, for that relation, it considers only points of Teichmüller space in the for the Teichmüller metric only as complex manifolds, complex surfaces. I don't need a metric. I don't need a metric on the surfaces. I'm measuring distances of the complex surfaces. Yes, you're right. Thank you. So I want to say another thing before I go to my PDF, to my slides. And this is about okay. You remember we had this notion of measured. Okay, no, let me start in this way. Let me start in another way. So I have a hyperbolic surface. I have closed geodesics. I remind you of this theorem, and this is called theorems due to Hadamard. I don't know, I would say 1920, something like that. Each simple closed curve, non-homotopic to a point, has a unique geodesic representative. In each homotopy class of simple closed curve, I have a unique geodesic. And then we said, in fact, yes, because if I have two curves on the surface which are homotopic, it means that there's a homotopy between them, and they are kind of bounded apart from this homotopy, and then I can lift the homotopy to the hyperbolic plane, and then the lift of the homotopy will give me a homotopy between two geodesics, which is not possible because they cannot be. They cannot be finite at finite distance. The geodesics are like this. Now, what I want to say now is that each measured foliation, not only each closed geodesic, has a geodesic representative. So this is on a hyperbolic surface. Let me justify this. This is complicated, but I want to give you the idea of how you prove this. Okay. I come back to a simple closed curve on the surface like this one. This is not a geodesic. And I said that there is a geodesic representative. The surface is hyperbolic. So I have the universal cover, which is the hyperbolic disk. And I look at all the lifts of this simple closed curves because this is simply connected. Every leaf will the lift of every leaf will be. So you see, the lift means I take a point here, I take a point here, which maps. I take a point here. I take a point in the universal cover, which is sent to this point. And then this curve, I traverse this curve, and I have one way of continuing here, just because there's a local homeomorphism from here to here, right, which is an isometry for this hyperbolic metric. And then I continue. I arrive to this point here. This is another lift of this point. And then I continue turning. I continue indefinitely in both directions. Now it is a theorem, not. I mean, you have to prove when you do this. You have to prove from time to time. You have to prove that when I do this thing, when I lift this curve, I converge to two definite points. From when I lift this curve, doing it from one side and from the other side, I converge to do two definite points on the boundary of the space. This is not trivial. It has to. This has to be proven. And I do this. This point has many lifts. So this is also another lift. This point, it has lifts here, but also it has lifts. You see, the universal covering is mixing many curves here. This is highly non-compact to this compact surface. So I have many lifts which must go here. This is infinite area. This is finite area. So, okay. So anyway, I lift, and then the thing which is non-trivial is to say that every lift, because in principle I could have a lift. Okay, I continue lifting, and then the lift will accumulate. Why not? Will accumulate, but this does not happen. This is hyperbolic geometry. Tells you, I mean, a few lemmas of hyperbolic geometry, which tell you that when I lift this curve, all the lifts converge to two definite points in the universal cover, and then I say, okay, now I'm happy because I know what will be the geodesic in the homotopy class of this curve. I replace each of these lifts by the geodesic that has the same endpoint, and I project again on the surface, and this projection will give me exactly the geodesic which is in the homotopy class of this curve. This is how you prove that, how you construct a constructive proof of the fact that each homotopy class of non-trivial curve is represented by a unique geodesic. It's not easy. I mean, if you don't understand, don't worry. I mean, if you want to understand this, you have to work a little bit. I can give references. Now, the thing which is a little bit more difficult, and which is, I mean, needed in this theory. Instead of a closed curve, I take a measured foliation on the surface. I take a measured foliation. a collection. You see, we always represented the measured foliation locally here. But one good question is, I will continue this sentence there. But one good question here: suppose I have a measured foliation, so I take one curve here, one leaf of the foliation, and then I continue indefinitely on the surface. The surface is compact, right? And then a good question is, what can I say about the limit, or what can I say about the closure of this leaf? So here I can continue. The closure of this leaf, it's a closed subset of the surface, but what kind of closed subset? And here you have, I mean, you have it's not, I mean, it's not difficult, but it's a natural question. And so for instance, do I have leaves which are dense in the surface? The closure of the leaf, can it be the whole surface? You think about the torus case. We discussed the torus case. When the slope is irrational, then the leaf is dense. When the slope is rational, then it's a closed leaf. And it turns out that in the case of arbitrary measured foliations, the closure of a leaf is either a curve, a closed curve, or it is a subsurface. Yes, a subsurface, and in this subsurface, the leaf is dense. It's a subsurface. It's not necessarily the whole surface, you see, because I could have, well, here a measured foliation on this surface, and here a measured foliation on this surface, and then I glue them, and the leaves here will never go to the other part. So there is this question of subsurface here. Anyway, so now you do now you do the same thing which I did here. Instead of doing for closed curves, you will do for the curves which are leaves of a measured foliation. Each leaf of a measured foliation, you will follow the, you will argue here in the upper half plane on its lifts, and you will show that each lift has two definite limit points on the boundary of my hyperbolic disk, and then you say, okay, I want to replace each leaf by the geodesic connecting the two limit points. I get a collection of geodesics, and since everything is compatible, you know, I'm doing this. So this is the universal cover of this. I'm doing on all the lifts. On all the lifts, I'm doing the same thing. So the quotient is something, a geodesic representative of my measured foliation. And this is called a geodesic. I didn't talk about the measure, but since I have here a measure, the result also is a transverse measured lamination, a geodesic lamination. Yes. What? Ah, okay. It's time for tea. Okay. I think I will not be able to do whatever I wanted to tell you. I'm a little bit sad for this, but I will tell you as much as I can for now with the slides. It will be more, it will be quicker, in fact, more effective. Okay, so we have tea now?
Yes.
Okay, let's go for tea.
You want a shorter tea break?
No, it's half. No, I mean, the students need to rest, and we will rest a little bit.
Yeah, I think we can ask questions.
Okay, thank you. Thank you again. I will start now. I will repeat a few things which I said in the first lecture. And now I think you understand them more because you are used to this. I will start with this definition of the Thurston metric. Yes, here. So this is associated with a surface S with genus G, and N, let's say, is the number of. We didn't talk about surfaces with boundary. We could talk about surfaces with boundary, but we talked about surfaces with punctures. So N is the number of punctures. Mm-hmm. So in this setting, in this hyperbolic setting, the punctures do not exist. In fact, they are at infinity. It's like when I glue two ideal triangles. You remember this, right? If I take, so this is my hyperbolic surface with punctures. If by puncture you mean something, well, I have a hyperbolic surface, then I remove one point. This is not, this is not so interesting, because then the surface will not be complete, right? We want complete surfaces. I didn't write it here. Complete hyperbolic. So no, because this when we say closed, it means compact without boundary and without punctures. But here I'm allowing punctures, like when I glue two ideal triangles with symmetric gluing, then I get this surface like this. Which is with three punctures, complete surface. Anyway, so this is the kind of surfaces for which the theory works. There's another theory for, an improved theory, enhanced theory, which is developed for surfaces with boundary. But this is I didn't have time to talk about this. You see, in the surface with boundary, with geodesic boundary, let me just say a few words. No, you don't need this. Okay, thank you. Can you see this? No, you cannot see. Okay, so please put it. Okay, so this is a surface which is this is compact with boundary component and with geodesic boundary. And you have to modify a little bit the theory to when you deal with these surfaces. For instance, for a surface without boundary, like this one here, we said that the simple closed geodesics play an important role, right? We dealt a lot with. Here, for surfaces with boundary, you have to include these. You have to include these arcs, geodesic arcs, which are perpendicular to the boundary. So it's a different theory. You have to deal with this. When you deal with surfaces with boundary, you obtain different theorems. There are new difficulties, which is very interesting, in fact. For instance, you remember we had, okay, so let me write here, it's clearer maybe. You did something? No, yeah, you can remove the water everywhere. Yes, even here you can. Yeah, yeah. So yesterday I talked about essential simple closed curves, and I said these essential simple closed curves means that they are not homotopic to a point. And somebody here told me to a boundary component also. I said no, to the boundary it's. I mean it depends, and I want to tell you something about this. Thank you, thank you. So. Suppose I have this geodesic pair of pants, that is, pair of pants with geodesic boundary components. I know that I have different shapes of geodesic pairs of pants. So I can make, we learned the other day that, for instance, I can construct this from right-angled hexagons, and I can vary the lengths of the right-angled hexagons, right? And I obtain different shapes of pairs of pants with geodesic boundary. And I want to do the whole theory. So this is a three-dimensional space. Three-dimensional space. Three-dimensional space since it is parametrized by the length of the geodesic boundary components. Okay? So I can do a lot of geometry in this three-dimensional space. I can try to find the geodesics of my Thurston metric or even my Teichmüller metric and so on and so on. So there is a lot to do with this space. Now, if I want to use simple closed curves, what are the simple closed curves here in the sense I said before? So all of them are homotopic to the boundary. So these are essential. I cannot ignore the simple closed curves, which are these boundary components, right? There are three of them. And then, just 1 minute ago, I was talking about arcs, and I said I mean, it's very useful to talk about arcs perpendicular to the boundary, and here they are, the three arcs, which decompose my pair of pants into two right-angled hexagons. And now I have everything. When I know the length of the simple closed curves, simple closed geodesics, which are only these three, and the three arcs, I completely know the geometry of the hexagon.
So is it a two-dimensional surface then?
No. I mean, no. The parameter space is 3 dimensions because I can parameterize either by these three lengths or these three lengths. So it's three-dimensional.
So it's just a length, not.
No, here there is no. Yes, just the length, just the length. So when I deal with arcs in general surfaces, I'm just interested in the length of these arcs. You remember we found a parametrization of the Teichmüller space of a closed surface by length of simple closed geodesics. Now for surfaces with boundary, it's a little bit more complicated because you have to introduce lengths of arcs. So this is one thing I wanted to say. But here, so here is SGN. SGN, let's say n is the number of punctures. We said that such a surface admits a hyperbolic structure. In fact, it admits any such, yes, the Euler characteristic, it must be positive. So I am excluding the sphere and the torus. And I'm excluding some surfaces. I'm excluding, what am I excluding? only the sphere and the toroid. So in principle, I want to exclude also the cylinder because it's not hyperbolic, but there's no cylinder since I told you the n here, the n represents the number of cusps. So there's no cylinder with two cusps. Okay. Anyway, so let's forget about the special cases. We.
The two typos there. 2 minus 2g minus 2n less than 0.
This should be less than 0?
Yeah, and minus n also.
Minus?
2 minus 2g minus n.
Okay.
2 minus 2g minus n.
Minus n must be less than 0. Okay, thank you. Okay, thank you. I'm sorry. Yes, I'm sorry. So you, this inequality sign is wrong, and here it must be.
No, the minus n.
Here it must be negative instead of positive. Maybe I also made a mistake in one of my papers, because yesterday when I was copying this from, I was looking at one of my papers and I copied this formula, but it's fine. I mean, everybody knows that I make such mistakes and you can correct. Okay. So S admits a hyperbolic structure. We talked about this, and we even said that S admits, as soon as it admits one, in fact, it admits a whole family of hyperbolic structures, not only one. It admits a space of hyperbolic structures, and this is the Teichmüller space which we are dealing with. We are studying precisely the space of all these hyperbolic structures. Okay, so this is complete finite area.
So this encompasses all possible hyperbolic structures?
All hyperbolic structures on such fixed surface, yes. Yes?
I have a question.
Okay.
So if you take a surface with boundary, it is not a cusp.
Yes.
Geodesic boundary.
Yes.
Then you still have a hyperbolic structure there, or it's more complicated?
Yeah, you still, on surfaces with boundary, there's this theory of hyperbolic structures with geodesic boundary, yes. The universal cover will not be H2, no, since you have boundary. I mean, you have the universal cover, you have to have local homeomorphisms. And if the surface has boundary, then the lift of this point must be something with boundary, right? So the universal cover will not be the hyperbolic plane, but something inside. Wait, yeah, some polygon with infinite number of sides sitting inside the hyperbolic plane. Yes. Yes. There was an important thing we talked about marking. The marking of a surface. The marking of a surface is, okay, homotopy class of so on, but let me tell you the essential things is that the marking of a surface, I'm always doing the same picture. The marking of a surface permits me to say that I'm considering this particular homotopy class of curves and not another one. So if I don't speak about the marking, well, I have a surface. This surface, there's a map, there's a homeomorphism from this map taking this curve to this curve. You see just the symmetry with respect to this axis. So how would so these curves are topologically the same, in fact, right? So how would I distinguish with them? I distinguish them with a marking. A marking, it's like I said, a homotopy class of homomorphism between a fixed topological surface. It could be something else. It could be just an isomorphism between the fundamental group of this surface with a fixed group, so that each curve I know precisely which curve is this, but from this fixed homomorphism between the two groups. Okay. So this is important thing, the marking. Yes.
You don't want to consider the plane, that the plane
No. This is this is another theory. This is a little bit of more complication, which I don't want. Yes, if I had 2 times the time, then I would have yes. And then we have this Teichmüller space of marked hyperbolic surfaces up to isometries that preserve the marking. We talked about this. If I don't put this up to isometries which preserve the marking, then I would have an infinite dimensional space. Okay, and now you must remember that this definition, we said that we have 2 marked hyperbolic structures and a homeomorphism, and then we have the Lipschitz constant of phi is something interesting. This is the Lipschitz constant of this homeomorphism. And then what did I write here? So from this definition of a Lipschitz constant, I want to the first question is, does there exist a homeomorphism with minimum Lipschitz constant? And again, you have some theorems. So you take you take a sequence. So the minimum exists. The minimum of the Lipschitz constant exists if you do the minimum above, over all homeomorphisms. It's in general, it's not. Nobody tells you that the minimum is realized by a homeomorphism, right? There exists, by general theorems of topology, there exists some maps between the 2 surfaces that realize the minimum constant, but why is this a homeomorphism? And what I'm saying here is that one of the results of Thurston in this paper is that in any homotopy class between 2 hyperbolic surfaces, there exists a homeomorphism that minimizes the Lipschitz constant. And he constructs such a Lipschitz minimizing homeomorphism. There are many, but he constructs one which he calls a stretch map. This is why the paper is called minimal stretch maps between hyperbolic surfaces. This word stretch map is highlighted even in the title of the paper. And okay, I'm giving you some of the properties of these stretch maps. It preserves a complete geodesic lamination. Forget the word complete, but today I explained to you what is a geodesic lamination. It multiplies the arc length on this lamination by some constant. This constant here, I didn't write it, but it is the best Lipschitz constant for the map.
So which arc is the transverse arc?
No, not the transverse arc. It multiplies the arcs along the lamination. The lamination is itself stretched by this constant. The transverse arcs, on the contrary, are contracted. It's like this picture of the map of the ideal triangle. You see that you have a dilatation here along the sides, and the transverse arc are contracted. The general construction of Thurston is a generalization of this construction for the ideal triangles. Okay, smaller than this constant. This is something. Now, and the Thurston metric. Okay, I have two hyperbolic surfaces. 2 hyperbolic surfaces on my topological surface S, together with the marking, and I declare the distance. This is the Thurston distance between the 2 hyperbolic structures as the logarithm of the infimum of the Lipschitz constant over all homeomorphisms that preserve the marking. Now I think if you concentrate, if you are concentrated on what I said, you understand all these words. You understand this definition. And L induces a function on a distance function on Teichmüller space, so a function on the product of Teichmüller space by itself, which is the logarithm of the infimum of this Lipschitz constant f, the infimum being taken on all the maps, all homeomorphisms that preserve the marking. The f here is this f here, all homeomorphisms that preserve the marking. And in his paper, he shows that this function L is a metric, except that it does not satisfy the symmetry axiom. We talked about such metrics, the non-symmetric metric. These metrics, non-symmetric metrics, in fact, are appear now in geometers. You know, many fields of geometry now use non-symmetric metrics, asymmetric metrics. They find it natural, like this Thurston metric. This Thurston metric, the distance from A to B is not necessarily equal to the distance from B to A. And this is...
Venkatesh also talked about this.
Okay. Yeah, thank you. Yes. I think Venkatesh also talked about this, the Funk metric. I think he mentioned this Funk metric. And in fact, these asymmetric metrics, the physicists, they are used to deal with asymmetric metrics. So they are, the non-negativity is necessary. The non-negativity is necessary. The metric must be greater or equal to 0. The non-degeneracy also, if the length, if the distance between 2 points is 0, then the metrics must be the same. And here is, I hope it's the right sign, yes. This is the triangle inequality. What is missing is just that the distance between h and h prime is equal to the distance between h prime and h. You see, it's like somebody going from the bottom of a hill to the top of the hill, where in some evident sense the distance from this point to this point is greater than the distance from this point to this point. You can measure it by the energy you take, and so on and so on. I mean, so natural. So distances between 2 points on the surface of the Earth, I can measure them. Say by the time a pedestrian needs to go from one place to the other, from place A to place B, they satisfy triangle inequality and so on. And if the distance is 0, it means just I'm staying where I am. But the symmetry is not natural. In fact, the distance from here to here will be greater than the distance from here to here. Okay, so this is just to justify this definition and this study of non-symmetric distances. So now I have, since this distance, I have defined several distances on various metric spaces which are non-symmetric, and then we study these non-symmetric distances. We study their geodesics, we study their isometries, we study their you can study properties of triangles in these metric spaces. You can study the properties of the circles. You see, circles in circles or disks in hyperbolic space, and also in Euclidean space. In Euclidean space, these disks are convex. You know what it means, convex. It means that if I take 2 points in this disk, then and the shortest path should stay in this disk. In hyperbolic space, we gave 2 models of hyperbolic space. Do you have this property? Yes, you have this property, but you have to prove it. if you take a disk in hyperbolic space, that is, you take a point and the set of all points which are at some distance less than d from that point, you find a set which you call a disk. And you ask yourself, I have a disk in hyperbolic space or in more general space. I have this disk and I take 2 points. And a shortest geodesic between these 2 points, is it necessarily contained in this disk? The answer is yes, maybe yes, maybe no. In hyperbolic space it is true and you have to prove it. In general metric spaces, you don't know. And so what I'm saying here is that you define some hyperbolic metric, you define some metric on some space, like the one Bankatesh told you the other day, and then you ask whether the disks are convex or not. If the proof is easy, then okay. If the proof is difficult, then you have a result. You have a result. Well, in that metric space, the disks around each point are not necessarily convex. Okay, and so the distance from A to B, the distance from H to H prime is not necessarily equal to the distance from H prime to H for the Thurston metric. And this picture now you are used, I showed you several times pictures taken from Thurston's papers. So this is supposed to represent, this is a hyperbolic surface. This is a hyperbolic surface, so he drew it. So here. So the 2 holes are here, and then I have a long tube along them. And I have a long tube joining them. A long tube of length A. So hyperbolic length from here to here is more or less A. You see, we mentioned that the area of a hyperbolic surface is fixed. The area of hyperbolic surface of genus 2 or genus 3 is fixed. So if I have somewhere a long tube, I take even a longer one, it will take a lot of area, right? But the result is that if I have, the more I take a longer tube, the more it must be thinner, because the area must stay the same. The more it must be thinner, and the more these pieces here, even if they have complicated topology, more complicated than just a tube, these must be, these become smaller and smaller because I'm taking too much area from this long tube. I mean, the tube is not a line; it eats some of your area. Okay, so this is his example, and he says that the distance, the best Lipschitz constant from here to here, the arrow here, well, this is more or less. We talk about Lipschitz maps from this surface here to this surface here, which is slightly longer. What counts here is the ratio of this distance here to this distance here, because the other distance will count less. This is what he says. From here to here, the Lipschitz constant is more or less B to A, but the Lipschitz constant from here to here, and this is now hyperbolic geometry. It tells you that hyperbolic geometry, I said that if you have a very, very long tube, it becomes thinner and thinner, and it becomes thinner by something exponential. The diameter here is exponential to minus A, where A is this, and the diameter here exponential to, well, for the same reason, it's exponential to minus B where B is this. And now, if you take a Lipschitz maps from here to here, then what counts is this ratio here, E minus A divided by E minus B, which is different from B over A. And this is why the distance is non-symmetric. This is an example for where yes?
So the analogy you gave about these higher and 2 points, right, on Earth. So are those related with this entropy, critical exponent? So
yeah, is it? Yeah, yes, it is related with. Yeah, I mean, yes, there are. I mean, yes, you use this. Yes, you use this estimate. Yes, yes.
So this lower distance between lower entropy to higher entropy is more than the distance between higher entropy.
Yes, right, exact. Yes, yes. I mean, there are physical systems where the entropy to go from here to here is not the same. Yes, yes. Yeah. It's related. In fact, yes, yes. I mean, I don't know much about this, but it should be related. Okay. So now this is something new I want to tell you. So we have a definition of the Thurston distance, which I told you several times, best Lipschitz map, logarithm of the best Lipschitz map from one surface to other. Now, there's another definition of the Thurston distance. You see, when you have a mathematical object, you define it in such a way, and then you say, I want to give an equivalent definition. If the second definition you give is substantially different from the first one, then you are very happy because you found a theorem, in fact, that one definition is equivalent to the other, and for this I need to work. So now, in fact, there are four different definitions of Thurston metric, and they are all different, and you have to prove that they are different, and these are theorems. So the second definition uses the space of the set of simple closed curves. The first definition is in terms of Lipschitz constants of maps. Now, you remember I explained to you that hyperbolic surface, I can characterize it by its length spectrum, the length of the simple closed curves, right? So if a hyperbolic surface is defined by its length of simple closed curves, well, I can measure a distance between two hyperbolic surfaces just by comparing the lengths of simple closed curves, right? It's a good distance between surfaces. And it turns out, and this is Thurston's one of his theorems, that you define a distance here, and the two distances are exactly the same. And this is the second definition here, which I will take. Okay, so we already talked about simple closed curve. We say that it's the image of an embedding of a circle into the surface. This is simple closed curve. And we said that we only consider essential curves, meaning that they are not homotopic to a point and not homotopic to a puncture. We don't want, you see, the problem with punctures is that, I mean, it's not a problem, but we ignore the simple closed curves homotopic to puncture because I can make it smaller and smaller and smaller, and its length goes to zero. I don't want to deal with such curves. When it's homotopic to a boundary component, then it's fine because the boundary component is an invariant of the surface. Anyway, so essential not homotopic to a point and to a puncture. And this also, I already talked about this set, script S. This is a usual notation. You know, all the people working on this theory will denote by S the set of homotopy classes of simple closed curve. If you write a paper and if you say, okay, I have a set of essential simple closed curve on the surface, and I denote it by E, and I'm reading, I said, well, why is he using a different notation than anybody else? This is the standard notation, which started by Thurston, in fact, and everybody uses it. S, the set of script S, homotopy class of tensor simple closed curves. And now, when you have a simple closed curve gamma, I explained the other time, and today also we talked about this, there is a unique closed geodesics in this homotopy, in the homotopy class of gamma, right? And then I can consider its length. And now, given two hyperbolic structures, you see, I want to compare the lengths above. I want to compare the lengths of the curves measured in H prime and the lengths of the closed curve measured in H. And in fact, the distance will be 0. I want to say that the distance is 0 if all the lengths are the same, right? We said that we have this theorem from what? Either from hyperbolic geometry or from spectral theory or whatever. It tells you that if the lengths of the simple closed curves are the same for a hyperbolic surface, then the surfaces are the same. So I take the supremum of this quotient here, the length for H prime divided by the length of H. If the supremum is equal to 1, it means that all of them are equal. And then I have to take log, in fact. The log is just, the log you need it because I want to define a metric. And the log is needed for the triangle inequality. The log here is not a meaningful thing. I mean, just for convenience. And then now you have a new function on H and H on metrics. This K defined on the product of the Teichmüller space with itself. K H prime is this, and then I say that K like L defines a weak metric. Weak means that it does not necessarily satisfy the triangle inequality. And I don't know whether this one, it is easy to see that it satisfies the other properties of a metric, and then you will know that it does not satisfy the triangle inequality because of because of this. I skipped something here. I didn't write it here, but K is equal to L. There's a theorem, in fact, by Thurston, which he proves in this paper, saying that this function K coincides with the Thurston distance L. I said just part of this thing that it defines a metric, but also K is equal to L. This is the second form of Thurston metric. And here, okay, I need the two together. Never mind. So so you see here I'm taking the supremum over all simple closed curves. The second form which I will give is instead of simple closed curves, I will put here measured geodesic laminations. This is why I talked today, in the first part, we talked about measured geodesic laminations. I didn't explain, well, I said more or less that an example of a measured geodesic lamination is a simple closed geodesics. Measured geodesic laminations are more general. They are obtained from measured foliations by replacing each leaf by the geodesic, which connects the two endpoints, which is the quotient of the geodesic, which connects the two endpoints in the lift to the hyperbolic disk, and so on. So here, you see, it's the same definition as before, but instead of putting here simple closed curve, lengths of simple closed curve, I'm putting lengths of geodesic, measured geodesic laminations.
Gamma can be multi-curve or?
It can be a multi-curve, yeah. It can be a curve with, in this formula. In the previous formula, no, but in this formula, a union of disjoint closed geodesics is an example of a geodesic lamination. And now, something which I mentioned last time about measured foliations, but the same, I mean, I explained to you that there's a natural one-to-one correspondence between measured foliations and measured laminations. Last time we said that the space of measured foliations is compact. It's compact and homeomorphic to a sphere of some high dimension, and it is the boundary, Thurston boundary of Teichmüller space. So in exactly the same way, the space of measured geodesic laminations, in fact, here, you see, the supremum, yeah, okay, let me just say, let me say something before. The supremum is over compactly measured laminations. We don't need the term compactly supported. And now we said that on a surface, so this is my surface, and we have something which is a geodesic lamination. It's something more complicated than a curve, but constituted by a union of geodesics, which may wander around the surface. Okay, so something I didn't say is that the simple closed geodesics, I gave you here a picture from Thurston here. This one here, geodesics which is wandering, simple closed geodesic, typical simple closed which is wandering, and which looks like a geodesic lamination, because I mean, now I'm telling you that it's a simple closed curve, but you cannot, I mean, if you just look at it like this, you don't know whether it closes up or not. And the fact which I'm saying is that you can approximate the geodesic, general geodesic laminations by simple closed curves. And this is what this says here. Density of weighted simple closed geodesics in the space of measured geodesic laminations, and the length function of the length of simple closed curve extends continuously to the space of measured geodesic laminations. So it means that the supremum here can be taken over, instead of the simple closed curve, it can be taken over the measured geodesic laminations. The fact that before we had simple closed curve, now we have this measured geodesic lamination. It follows from these two things. And then now the third thing is that I can replace the space of measured geodesic laminations by the projective measured geodesic laminations. That is, measured geodesic laminations defined up to a constant, because the same constant will appear here, and it cancels. And now this is very important because when I take the projectivization, and this is something I told you last time, the projectivization of measured foliation space is compact. And when you take the supremum over some compact set, there is a point which realizes the supremum. So here is what I'm saying here. The supremum can be taken over projective compactly supported laminations, where I did. Okay, so here the supremum, instead of ML, I have a projective ML. By compactness, the supremum is attained, and then this tells me that when I take two random hyperbolic surfaces and I look for the best Lipschitz constant of mass between them, there is, in fact, because the supremum is attained here, there is a maximally stretched lamination. There is I can find a lamination which is maximally stretched, and this is a fact which Thurston uses to show that for any pair of points there is a geodesic joining them. Once you find that there is a measured geodesic lamination on which the supremum is attained, then it is this one which you have to stretch to go from to find a path which a geodesic path which starts with this surface and goes to the other surface. So this is what I said. I'm simplifying. You see, I'm saying a lot of things in a few, in half an hour, but I'm obliged to say this. So this fact is used to prove that for any points in the Teichmüller space, there's a geodesic joining them. Okay. And now I want to tell you something about this metric of Thurston, which is K and which is L. I explained to you that K is equal to L. K is with Lipschitz constants, and L is with comparing simple closed curves or laminations, or whatever. I am telling you that this is a Finsler metric. Somebody asked me a couple of days ago whether this is a Riemannian metric. I said, no, this is a Finsler metric. And let me tell you again what is a Finsler metric. Let me tell you again what is a Finsler metric. Okay, Bankatesh talked about the Finsler metric. Yeah, I can say a few words about Finsler metric because I want to mention, you see, there are some books on Finsler geometry which I do not want to mention. I cannot give the name because I want to say something about it. So I open this book. I don't see at all what he is talking about. These books are full of tensors and calculations and whatever. Worse than anything I can read. But the subject of Finsler geometry is a very geometric and very easy subject and very natural subject. You don't need all these calculations. It is simply the following thing. This is a metric space first. A metric space satisfying the properties of a distance function, except that the distance from x to a or distance from x to y in general maybe not equal to the distance from y to x. So we remove this symmetry axiom because, as I explained to you, in some cases, like in the Thurston metric, the symmetry axiom is not satisfied. And how is this metric defined? How is this metric defined? In fact, the metric is defined. The distance between 2 points, the distance it's the minimum of the length of curves joining them. It's a metric where the distance is equal to the infimum of lengths of curves joining them. So now we're not, I didn't tell you anything important about this metric because now you'll ask me, okay, but how do we measure the lengths of curves? in some space, like in this Thurston. Well, this is where the name Finsler comes. You have a differentiable. You have a differentiable manifold. So suppose. So let's take a very easy example. Your differentiable. Your differentiable manifold is just a disk embedded in the plane. There's no metric. I'm going to define the metric. And then I tell you the distance between 2 points is infimum of the length of the curve joining them. So I take a curve here. I measure its distance. I take a curve here. I measure its distance. And then I take the smallest of these lengths. But I didn't tell you how I measure these distances, right? So in the Finsler manifold, at each point of the manifold, you have a convex set. This is the main point. So you know what is a convex set in the plane. So for instance, I decide that okay, I take one example of a convex set in the plane is this equilateral triangle. It's a convex set in the plane. And I take the same, at each point you have a convex set. I'm taking this same equilateral triangle at every point, centered at this point. And then I tell you that this convex set is the unit ball of some norm. You have studied norms, right? You know that to each norm, to each norm function, there's associated a unit norm, which is, and that the unit norm is convex. Usually, it follows from the properties of a norm that its unit norm. So this means that you see. So take this point. At each point, you have a convex set, which you declare to be the unit ball of some norm, and it means now that at each point I can say what is the measure of a vector, right? Since I know what are the vectors of norm 1, so for any vector I can see how much for any vector here. If I have a vector which is very long, this is my vector of norm 1. Since this is, and then I can see how many of these intervals, maybe there will be a fraction of it, and I can measure the length of this. I can say what is the length of this vector, right? The unit ball of a norm permits me to say what is the length of any vector. And now here at each point you have a convex set which you declare to be the unit ball of some norm. And now you take 2 points. You take 2 points, any 2 points. You join them by a differentiable curve. You join them by a differentiable curve. And you can say what is the length of this differentiable curve, because this differentiable curve, it has tangent vectors because it is differentiable. At each tangent space, you can say what is the norm of the vector tangent to this curve, right? So you find a number, and then you take the infimum over all the differentiable curves joining these 2 points. So this metric here at each point, so the distance, okay, the length of a curve, this I know how to compute because I have this family of convex sets. So I know how to compute the length of a curve because of a differentiable curve, because a differentiable curve has tangent vectors, and I can measure the length of each tangent vector, and I take the integral over this curve. So I find the length of this curve, right? You understand? And now I say that the distance between 2 points is the minimum length of the curves joining them. Simply this. And this is all you need to know about Finsler manifolds. And then you have, again, a lot of new open problems. So one problem which you can, okay, you take a set. You take a subset of the plane if you want. Let's take an ellipse, or let's take a circle. Why complicating? Let's take a circle. Let's take a circle. Let's take a disk in the plane. This is my surface, and I have millions of ways of defining a Finsler structure. I explained to you that a Finsler structure is just you are just given a field of convex sets, right? So let me say that, okay, I will take as a Finsler structure, I took triangles, but let's complicate a little bit. So here I have all these, at each point of this diameter, I have these triangles. And then, okay, slowly, I will make the triangles. I will make the triangles look more like on each of these lines here, and here even greater on this third line, until I arrive to the boundary. I can make them larger, or I can make them infinity when you arrive at the at the boundary. Since I'm only interested in the open disk, I have a metric. In fact, this defines a metric on the disk. And my question now is, okay, can you describe the geodesics for this metric? Can you describe the circles, the geometric circles for this metric? What are the curves which are equidistant from a point? No, it's not the convex set itself, because the convex set is in the tangent space. In principle, there's no relation between this convex set and the circle around this point. So you have a variation of millions of variations of definitions of a Finsler structure. And then the question is, I have 2 points. There, in fact, from the definition of the Finsler structure, you know that they are joined by I mean, no, you don't. Why is this? You want to show that between each point you have a shortest curve. What is this shortest curve? What is this shortest curve? Is it unique or it's not unique? And other questions like that. I mean, I could spend hours explaining good problems in Finsler geometry, which I cannot. There's this. I mean, I don't have the time to do it. So let me mention just there's this. Where is my thing? Ah, it's here. Mm-hmm. One good example of a Finsler manifold is this, you take a convex set, see, this convex set, it could maybe it has some line on the boundary. This is tautological Finsler structure. So the term tautological, comes from a Greek word. It means I'm taking the same thing, and you will see why. I'm taking a convex set, and I want to define a Finsler structure on this convex set. So again, what I need is to define at each point a convex set, right? So at a point here, I take as a convex set in my tangent space. You see, this convex set will be the unit ball in the tangent space. I take the same convex set as here, the same convex set, but centered at this point. So it will be you see, at this point, the tangent at this point, which is this center, more or less, I take this convex set. The tangent plane is identified with the plane. This is I mean, in the Euclidean. I mean, this is the tangent space. There's a I mean, I can visualize it as this plane, and at this point here, let me explain this in other words. At this point here, I want to choose a convex set in the tangent plane. So I choose this convex set itself. At this point, this is a point on the set. Again, I want to choose this convex set as a unit ball in the tangent plane, but now the center is here. So this will be, when I think now in the tangent space, this will be a unit vector. 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 So this is my tangent. This is my convex set in the tangent space at this point. Whereas at this point, again, the unit ball in the tangent space is this set itself. But this is a unit vector. 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 So the two unit balls are completely different, even if I am choosing the same set, because the center is different. If I take this point, then these will be unit vectors. These will be unit vectors, and so on. So I have a completely new geometry here. I have a new world, and I'm asking you, okay, you have this Finsler manifold. The good questions again are describe the geodesics, describe the circles, describe anything you want, the triangles, and see if the triangles define some hyperbolicity condition, which I didn't talk about, but these are good questions. So this is a Finsler, and I want to finish now. I had too many other things which I will tell you I cannot. The thing is that Thurston's metric is a Finsler manifold, and Thurston gives a description of each of the Finsler space of projective measured laminations. And this is, I think, is really fantastic because, okay, this is very interesting, but it's artificial, you know, because, okay, I took a special, I mean, it's very interesting to study such metrics, but okay, why take this shape and this one and so on? But here in the Thurston case, the unit ball at each point has a geometric significance. It is the space of projective measured laminations on the surface. And then there are many things, once you know this, to study the symmetries of this metric, the isometries of this metric, the geodesic of this metric. Now that you know that it's a Finsler metric, you have much more interesting basic things to talk about and to use. Okay, I think I will stop here.
Any questions, comments on the course?
You given the equivalent definition. You get the equivalent definition. Right?
There were two. The 1, 2, and this is.
With the measured lamination.
Yes.
So how to define the length if the curves are not closed? So,
the lengths of measured geodesic laminations.
Measured lamination.
Yeah.
The curves are not closed.
Yes, you are right. I mean, you have to. Yeah, that's a way of defining them. The length of a geodesic lamination, of a measured geodesic lamination, is defined even if the curve is not closed. I mean, it's not easy, but it's not difficult. But there is this is a basic thing in the theory: the length of a measured geodesic lamination, even if it's not a closed curve. You have to integrate. There's an integral.
All curves are finite length, you're saying? All the leaves of the measured lamination?
No. There are infinite leaves. But yeah, I see where's the problem. You are not adding the sum of the lengths of the leaves. It's something more complicated.
It comes from
You use the transverse measure. You see, let me just say it in a few words. So you have a geodesic lamination like this. You see the leaves may be closed or not closed. You have to cover it by some boxes like this. On this side you use the transverse measure, and on this side you use the length, the curve length, and then you add over. It's independent of the way you cover the surface.
So when the geodesic is like spiraling, we take the transverse measure, and when it is not?
When it is spiraling, there is no transverse measure. This is the problem. Because it's not a measured lamination if it's spiraling. There's no invariant transverse measure. You see, when you have a spiraling like this, then you take a segment here, and you make it spiral along the fish here. You want to send, and then these to these, and then the rest. And the question is, No, yeah, this is something else. But I want the distance in the Thurston sense. That is the Thurston distance, one using the best Lipschitz map, and the other should be, in fact, the ratios of these distances, these distances, and the radii of the circles or things like that, you see, or if these are ellipses and so on. You can complicate a little bit. And yes, this is a very good problem, in fact. In fact, as I told you once, I wrote several papers, triangles, just on the space of triangle. The Thurston metric, maybe now you understand more where are the difficulties. The space of triangles in the plane. Define the Thurston metric and see whether you have the two equivalent definitions and the geodesics. So the geodesics are characterized, you pass from one triangle to the other by a geodesic if and only if, I mean from that paper we had if and only if the angles vary monotonically. So two are decreasing and one is increasing, for instance, and monotonically. If you destroy the monotonicity, it's not a geodesic, and so on. So this is the first paper I wrote on this with a young postdoc who came to Strasbourg 2 years ago. No, it was longer. It was during COVID. In fact, he came, and we worked on this. Yes. Yes.
Teichmüller metric is symmetric, and
yes, the Thurston metric is not.
Thurston metric is not
This is a very good question. How do you see the compactification of Teichmüller space when you instead of thinking about the Teichmüller metric, you think about the Thurston metric?
That's at the boundary.
You cannot. No, you don't. You don't arrive to the same boundary. But it's a good question. How do you compactify? Yes.
It's if you're going towards the boundary.
It's a partial compactification. In fact, yes. You cannot really attach the whole the whole sphere of measured geodesic laminations. Yes. Yeah. This is a very good question. Yes. To define compare also the various boundaries, yes.
So because the Thurston metric is asymmetric, can we say for certain that this fish came before this fish or something like that?
This is what I can suggest, but as I told you, I mean, biologists should yes. We don't know enough, you know. On biology, but some biologists would, if you discuss with them, maybe they have ideas on this. I mean, this evolution takes millions of years, and there are conjectures, but we will never be sure. Yes. What?
Good reference on Felsner geometry, not the geometry inside.
Busemann's paper, the papers of Herbert Busemann. He has, in fact, he has a paper with the title Finsler and things like that. Yes, it's without tensors, without calculations. Yes.
Sir, you have talked about the singularities.
Yes.
Yeah. So, is there any way like we can remove it, like we see in some complex analysis?
Yeah. Okay. So you see, I didn't go into the details, but it's when I talked about singularities of measured foliations. So this is a singular point like this, and then there's an equivalence relation on measured foliations. This is. You see this singular point. I replace it by this small interval, and I get two singular points instead of one, but of simpler structure, because here I have 4 separatrices, here I have 3 and 3. So this is, but you cannot remove the singularities, no, because of Euler characteristic of the surface. You will always get singularities.
Okay, I think you can also discuss maybe later after we have the closing. Let's thank Professor Papadopoulos for this talk and the talks every day. It was a wonderful course. The way he did hands-on would have given us more information. I learned a lot. I don't know anything about these topics. Only what I have learned is I don't work on it. So, and I'm sure for young students it was very useful because you know, he didn't go into too much technicality, so you get some ideas, and I think that is a good way of running your course because you can't reach. I mean, you have to reach, you know, try to reach also some of the younger people, so it works, so they get inspired to do this course. I'm very glad that he gave this set of 4 lectures. It has been like, you know, 14 hours in a week is a long time, and he came only just Sunday early morning, Sunday night, Monday early morning, and started the course, and next week again we go to Calcutta. So we are very grateful to him that he agreed, and he very enthusiastically delivered this course, and you can take you know, it further by learning things from books. You can also write to him, discuss with him, ask questions. And I'm hoping that all of you will get inspired to do geometry. A lot of courses we do don't have so much geometry, it has more other topics. So I, for one, is very happy to see so much hands-on geometry. Gives you some idea how things have worked out. Unfortunately, for a master's program, we don't have any course in geometry. And I would like to thank the volunteers. We have 4 volunteers: Devmita, Sumit, Ravi, and Himanshu. They have been the backbone of the program. So is the office staff. You know, you've seen Manoj, you've seen Saurabh, you've seen Ashish, and others in the background. They have all been working on this. I would also like to thank the coordinator for the GAN program, Professor Satyavrat Patnaik. You saw him on the first day. I think he's probably left, I don't know if he's around, but he has been helping us to run this program. I'd like to thank this live studio moving team. There are 3 of them, and they have been presenting it to the YouTube participants, and they have done a good job. You can also, so these courses will remain online either through that link, or you can go to JNU GAN website and you will find there is a YouTube on that website, and you can go back and learn again whatever you missed or you want to learn again. And last, I would also like to thank the audience who, and many of you took active interest, and I see my MSc students who have diligently stuck to this course, and also MSc second year also were there until yesterday to their gate exam, so they could not come. And you want to clap it for yourself? I will clap for you. And I would, last but I mean, we also had 2 other people who gave a course. Professor Krishnendu is here, and also Professor Venkateshwar Tiwari, and that gave us a different flavor of related areas. And Krishnendu, do you want to say anything?
Yeah, I want to thank you for organizing this conference.
It would have been possible without everybody's support.
I would also request to follow it up, maybe another kind of.
Okay. And last but not least, I would like to invite Professor Professor Sogun Sen, and a big thank you to him for all the support and technically and everything, and so he's part of the team.
No, but anyway, so I think it's part of every team that the head of the school has to do. And first of all, obviously, we should thank.
We must thank Professor Papadopoulos for coming here and giving this, very strenuous session of 6 days total, starting from Monday till Saturday. And quite nice to see in Saturday also you have a lot of participants over here. And we were just discussing during the tea time with Professor Papadopoulos. He will he'll be missing you people now. In fact, he was teaching for some time, and he said that I'll be now started missing all my students whom I taught for the last 6 days. And that's the kind of a connection that you always make in general. And this GYAN program also gives you this privilege to explore more, because all these lectures and talks have been uploaded in the GYAN website, so you should really go back. So you may have missed out something or the other, and you can always go back to those videos and really see, and then again get back to him. And I'm sure that there are many other people also here who have also given talks. I think you have given talks, others have given talks over here, so they are also here. And I also got to the last part of it that you were showing some fish pictures and everything, and you also mentioned that this evolution actually made so much of changes and so on and so forth. So we should also interact with the biologists. So that's something quite interesting. Yes. So really, that's the thing that we should appreciate on all these surfaces and geometries that we want to learn in many, many different things that we have it around us. So anyway, thank you very much for making this a very successful event. And I'm sure that it will continue to go and so along. I'm sure that this is many more times he's going to visit JNU also, because he's a regular visitor to India, and we will again welcome you again for other events in School of Physical Sciences. Thank you very much, and thank you also to the organizing team for putting up this show very, very nicely. Thank you. Thank you.
So I'd like to thank also my colleagues who have been supporting by being here, attending, and also giving advice and doing various things. So thanks to them, also our JNU staff and Vice Chancellor, HRDC, guest house in charge, who really worked very quickly to give us accommodation. And I also see some local participants came from very far, for example, SNU, and they have been coming every day for long time. Good that you are here, and I'm really happy to see that you have stuck till the last day. So, yeah. And I would like to ask Professor Papadopoulos to speak a few words.
Okay, so I'm glad and I was honored to teach you, and I wish you success in mathematics and in your life. And I think I will see you, some of you I will see in 2 weeks in Bangalore, 2 or 3 weeks. Other I see regularly in Banaras, because I like to go to Banaras. And yes, I will remember your faces, and I hope I will see you again. Thank you.
So with this, thank you again, Professor Athanas Papadopoulos, and thank you everybody, and we close this session, and if you have few questions, you can ask him again.